everyone, and welcome back. Today we're going to continue our investigation of multiple linear regression, and we're going to actually make our own function that does a lot of the things that we've done up to this point. In case you have sort of investigated, some textbooks or maybe some other references, there's this function called LM, which often has a lot of these features that we've actually been working with so far. So what we're going to do today is we're going to write our own LM function. I'm going to call mine LM function or Nemo LM function, and it's going to do a lot of the things that we've done up to this point. For example, calculating our R squared adjusted values, p-values, condition numbers, point estimates for our regression model, and several other things as well. And once we're done making our little function, then we're going to go ahead and figure out how to calculate variance inflation factors and also how to create added variable plots with our newly created function. So let's get started. All right, now that we have our Nemo LM function written, let's just go over just a couple things that I want to make clear just in case you aren't familiar with them. The only thing that I haven't done up to this point is include this if is null portion of our Nemo LM function. So what the dim function does, in case you don't remember, is it returns the dimension of a matrix, right? And this matrix, or this structure xk, is going to be the set of all of our explanatory variable data, like x1, x2, x3, down to, say, xp. And y is going to be our response vector. So the number of columns in y by default should be equal to 1, and the number of columns in xk can be anything from 1 to down to, say, p. Now the dimension function will return the number of rows and the number of columns. That's why I'm referencing the second output of the dimension. But if xk is only one vector with one column, the dimension function actually is going to return a null value. So if the dimension function returns a null value, then we need to tell it, okay, the number of predictors in my model is going to be equal to 1, else is going to return the actual value for the value of p for which I want. So that's why I have this little error catching if-else statement in this function, just in case you're curious. All right, so let's just put in our finishing touches on our Nemo linear model function by returning the values that we want to our user. So the easiest way to return multiple values to the user when they call our function, similar to the SVD function, is to use what is called lists. So we're going to call our list results, and this list is going to contain all of our values. So the first value that I want to return is going to be the predicted values. I'm going to call that reference name pre, and that's going to be equal to our y hat values. The next value that I want to return is going to be equal to the residual, which I'm going to call res, and that's going to be equal to resid. And then we're going to have the standardized residuals, and that's going to be equal to sresid. And then we're going to have k. This is going to be our condition number, or the square root of the condition number of xtx. And we called that, what do we call that? Let's just go back and make sure that it's the same name. So we called that kappa. And then we're going to return LEV, so that's the leverage, and we called that LV. And then we have our SSE. I believe we called that capital SSE. And then we have, for example, our SSM. Then we have our MSE. And then we have our MSM. Usually we do not need to return the SST and the MST. Usually those are very simple calculations. That's just the variance of y and the variance of y times the degrees of freedom of y. So those just take up memory because they're easy to calculate in their own local environment. Let's return the p-value that we calculated for the appropriateness for this model. So that's going to be p-val. That's what we calculated up here. Let's also return the beta hat values. Let's call that beta hat. And we call that beta hat in our script. And then we have the standard error for beta hat. And we called that, let's just make sure it's the name. So it's capital SE beta hat. And then we have R2, that's going to be our R squared value. And then we're going to have, lastly, our R squared adjusted value. So R2 adjusted. All right. Once we have our list already created, then the last thing that we need to do is return this list to our user. So once we feed our function, our response variable y, and our sets of columns for our explanatory variables x, then the last thing it's going to do is return all of these values that we have in our list, right? And that is our Nemo LM function. Pretty neat, right? And it's going to do pretty much the same thing as the LM function, but now you can create your own and even add several other things to this function if you desire to. Now let's put this function to work. Now that our function is all created, what I've gone ahead and done is create these artificial explanatory data sets. I've called them x1, x2, and x3. So we're going to have 3 predictors, and we have a single response vector y. Make sure all of them are the same exact size, else of course we can't perform our standard analysis, right? And of course I've chosen my explanatory variables to be normal. I've let my response variable be uniform. You can make these whatever you want, or you can even use real world data if you desire. Right? So let's see if our function is created. So the very first thing that we need to make sure is that our function that we just finished writing is saved and everything is working. So let's just make sure we didn't make any errors. So the first thing that we need to do is bring our function into this environment. So let's just make sure these x's and y's are well defined. So let's put them in our environment. And then let us source our function that we just created, which I called nemolm.r. And that's going to bring in our function so we can use it. And the first thing that I want to do is create my models, okay? So the first model that I want to do is I want to regress y on variables 1, 2, and 3. So it's going to be model y regressed onto 1, 2, 3. So how do I use this function? So it's going to be Nemo LM. I'm going to feed up my response vector y, and then I'm going to feed up my vectors x1, x2, and x3, the 3 vectors that I want. and then I'm going to run it. So what's it going to return? It's going to return a list of 14 values. So let's just see what those values look like. So notice it's going to give me my predicted values, residuals, standardized residuals, condition number, leverages, SSE, SSM, MSE, MSM, p-value, our parameters for our linear model, the standard errors associated to them, our R-squared, and our R-squared adjusted values. Keep in mind, this is not the only model that we could use. We could regress y onto any combination of these variables 1, 2, and 3. For example, we can leave out 1, we can leave out 2, we can leave out 3, we can leave out 2 and 3 and just use a simple linear regression with y versus 1. That's perfectly fine. So how would we do that? So for example, if we want to do a partial model, for example, y regressed only on 1, 2, we can do Nemo LM of y regressed on vectors 1 and 2. We can do my regressed on 1 and 3. So it's going to be Nemo LM and then y and then c bind x1 and x3. And then we can do my with 2 and 3. And then that's going to be Nemo LM y c bind x2 and x3. Okay, so that's going to be our partial models. Now there's going to be 3 other models that I'm actually going to be working with because we need these for the added variable plots a little bit later. So that's what we get when we regress y against 2 and 3. So it's going to be Nemo LM x1 regressed against x2 and x3. And then we're going to have model 2 regressed against 1 and 3. So x2 against 1 and 3. And then finally 3 regressed against 1 and 2. So Nemo LM x3 regressed against 1 and 2. Okay, so we're going to need those 3 models for our added variable plots. So now that we have our partial models and some hybrid models, now let's go ahead and calculate the variance inflation factors for each of these variables, variable 1, variable 2, and variable 3. So how are we going to calculate a variance inflation factor? So remember, the variance inflation factor for, say, variable 1, I'm going to call that VIF1, is going to be 1 divided by the difference between 1 and the R-squared value associated to our full model, regressed y against 1, 2, and 3, but remove 1. So if we remove 1 from our full model, we're just left with 1 and 2. So the variance inflation factor is 1 divided by 1 minus the R-squared value for my reduced model when I remove variable 1. So it's going to be the model that's only leaving with 2 and 3. Okay, so let's reference our model, my 2 and 3. So it's 1 minus that. And then we need the R-squared value from that model. So we do $, and then you can reference any of the values for which we put in that list, right? And we want the R-squared value, and that's going to be that. So that's going to give us the first variance inflation factor. So the variance inflation factor for variable 2, that's going to be 1 divided by 1 minus the variance of the R-squared value of the model when we remove variable 2, which means we're just going to be left with variables 1 and 3. Again, we want the R-squared value from that. And then lastly, the variance inflation factor for variable 3 is going to be 1 divided by 1 minus my divided by, what do we get when we remove 3? We're just left with 1 and 2, and again, we want the R-squared value. So those are our 3 variance inflation factors. Now what I want to do is I'm going to store these variance inflation factors in a nice little vector. Let's call this vector VIF. And this vector is going to contain, for example, VIF1, VIF2, and VIF3. Let's create a nice little bar plot that actually displays the variance inflation factors, okay? So let's use a little bar plot. So a bar plot with these variance inflation factors. And let's make this a horizontal bar plot. And this is going to contain the variance inflation factors. And let's give these bars different names. So we're going to do names.arg. Right, so names.arg is going to give the names to each of those bars. So that's going to be equals, and then you give them their names. So we're going to do the same exact order for which they appear in this vector VIF. So 1, 2, and 3. So it's going to be x1, and then x2, and then x3. So those are the names. And now what I want to do is I want to create the limits of this bar. So XLIM is going to be equal to, So technically speaking, the smallest variance inflation factor for which you could have is 1. That's if your r squared value is equal to 0, right? So 1 divided by 1 minus 0, that's just going to be 1. Um, and then the largest value technically is infinity. But remember, a large variance inflation factor is really bad. So some people choose 5, some people choose 10. It really depends on what your threshold value for how large of a variance inflation factor are you willing to allow. So let's assume we want to use 5 as our cutoff value. So let's start off at 0 for our axes, and then let's go to the maximum of our cutoff value plus some distance a little higher than that, or the maximum of our variance inflation factor, right? So we have a couple scenarios here, right? So scenario 1, all our variance inflation factors are super small, which in our example they are. So this is going to go way past 1 and go all the way up to 6. So we're going to see all our bars are going to be relatively small to our cutoff value. Let's actually draw a vertical line at that cutoff value of 5 so we can sort of compare the distances. So if we have any bar graphs that sort of go past this vertical line, that means that variance inflation factor is significantly large with regards to our standards. So in order to do a vertical line, we can do AB line, vertical at x is equal to 5. And let's do this color in red. And in terms of the line type, let's do long dashes. Okay. So once we have this structure and all of our VIFs are defined, so what we can do is we can do our bar plot. Right, so there's our bar plot. Let's just stretch our windows so we can see what it looks like. So there's our bar plot. They look pretty nice. And let's put our little dashed line there. And there's our dashed line. So at least by this picture, all our variance inflation factors are significantly small. Therefore, we don't have, at least from the variance inflation factors, evidence to believe that multi-collinearity exists between our explanatory variables, which is a good thing. The next thing I want to do is create the added variable plots for variables 1, 2, and 3. Right? So how are we going to do that? So remember, the added variable plot, for example, for variable 1, is going to look at the standardized residuals for 2 different models. The first model for variable 1 added variable plot is what we get when we remove variable 1 from a model. So that's going to be y regressed onto 2 and 3. And then we're going to compare that to the standardized residuals of 1 versus 2 and 3. Because if the parameter beta 1 for our full model is equal to 0, then my23 and m123 should be the same exact model. So if we do not see a correlation between these data points, that is the points or the standardized residuals versus each other are completely random, or our correlation is 0 or our line is pretty flat, that means variable 1 is not contributing significantly to our full model 1, 2, 3. All right, so that's how we are going to interpret added variable plots. So how are we going to do that? So we've calculated all of our partial models and even the hybrid ones, so that's why I calculated these 1 versus 2, 3, 2 versus 1, 3, and 3 versus 1, 2 models. Right? So the first plot I'm going to do, so I'm going to plot model 1 versus 2 and 3. Okay, model 1 versus 2 and 3. And I'm going to get the standardized residuals from that model, so SRES. And I'm going to plot that against MY 2, 3, and then the standardized residuals of that model. Now you can reverse these two. Some people prefer the MY23 on the vertical axis instead of the horizontal, but the interpretations will be the same. Just the graphs will be a little bit rotated. Then I'm going to give this a name. So this is going to be the added variable plot for variable x1. And then I'm going to label the axes. So the x label for me is the standardized residuals for x1 regressed against x2 and x3. So that's the x-axis and the y-axis. And then the y label for me is going to be the standardized residual for y regressed against x2 and x3. Okay, so those are our labels. So we know what we're looking at, right? That's a good thing. So there's our added variable plot. We don't see any pattern between these standard residuals, which is definitely a good thing. So what are we comparing these to? So we're going to be comparing them to a horizontal line, and we can include that line via AB line 0, 0. So remember, the first is going to be the intercept, the second parameter is going to be the slope, and then LWD to be equal to 2, so we can see that line. So there's a horizontal line. And now let us draw the line of best fit for these standardized residuals against each other. So what is the slope of the line of best fit for each of these? I'm going to call this M1. So that's going to be R times SY over SX. So it's going to be the correlation of these two vectors. So I'm just going to type that. So the correlation of that versus the correlation of this other vector times the standard deviation of y divided by the standard deviation of x. Okay. That's one reason why I prefer my y versus 2, 3 to be my y component, because at least it makes a little bit more sense to me in terms of this calculation. So that's going to be the slope of my first line of best fit. Now I'm going to calculate my y-intercept. So that's going to be y bar minus mx bar. So y bar is going to be the mean of that value. Y bar minus m, which we already calculated, times the mean of x bar. Okay, so that's our slope and our intercept of our line of best fit for these residuals. Now I'm going to plot this in a different color. So we can do AB line of B1, remember intercept comma slope, and then we're going to color it whatever color you want. Let's assume we want to color it in red, and then a line width of 3, and that's going to give us our line, right? So our added variable plot doesn't say that, you know, it's a perfectly flat line or close to flat. We do have some evidence to believe that parameter beta 1 is a slightly negative, right? It's not harshly negative, but it's definitely some distance away from 0. You can of course do a hypothesis test and a statistical test on that, but according to this added variable plot, we have a weak negative contribution of variable x1, right? And that's the code for added variable plot 1. Now what we're going to do is we're going to copy and paste this code for variable x2 and x3, and of course modify appropriately in each of them. So what I've gone ahead and done is I've just copy and pasted the code that we wrote for added variable plot 1, but I've just gone and done it for 2 and 3. And I've just changed the variable numbers up just a tad bit, right? So this was our graph for added variable plot 1. For my particular data, these are the added variable plots for plot 2 and also for plot 3. So let's just briefly talk about how to interpret them. So notice that out of these plots, added variable plot 1, 2, and 3, added variable plot 3 has the most steepest line amongst all these three. That means added variable 3 is contributing the most to our model. In particular, we have strong evidence to believe that its parameter is negative, i.e. it has a negative contribution to our model or response values of y, right? And if we look at, for example, variable 2, that has the most shallowest line or most close to horizontal line. So we have evidence to believe, at least in comparison to like x1, that x2 is contributing the least to our model. So if you want to remove any variables, for example, based upon like multicollinearity or the variance inflation factor, if that line is practically 0, removing it probably is a good thing to do. Of course, every time you plan to remove variables from your model, remember that you are going to have removed variable bias, or omitted variable bias as some people call it, when you start removing variables. So only remove it if you really, really have to. So we have our variance inflation factors and our added variable plots. Another diagnostic that we always usually look at before we start, interpreting and using our model for predictions is correlation matrices. So we've already done this before, so let's just do a quick review. So a good library that actually does correlation matrices for graphics is CorePlot, right? So you can just run that code just to make sure your environment does have CorePlot already installed. And what we're going to do is we're going to create a correlation matrix. So this is going to be equal to core, and then we're going to cbind y, x1, x2, and x3. So that's going to be our correlation matrix. And then we're going to do core plot that correlation matrix. And then one pretty type of picture is the circle method. Right? And that creates a picture like this, right? Now, some people don't include the response vector y into this correlation matrix. That's perfectly fine. Some people only look at the explanatory variables x1, 2, and 3 versus each other, okay? And keep in mind, this is a symmetric matrix, so technically you only need to look at this upper panel or the lower panel. You don't usually need to include both, right? So, of course, as long as y has a strong correlation between x1, x2, and x3, then that is going to be a very good thing, right? So notice that we have a negative correlation or a moderate negative correlation with x1 and a strong negative correlation with x3. Notice that that's actually a very similar interpretation as our added variable plots had, which is a very, very good thing. What we do not want is the correlation between our explanatory variables to be significantly large. So notice that x1 and x3 have a practically zero correlation between each other, which is very, very good. X1 and X2 have a weak negative correlation, and X2 and X3 have a weak positive correlation, right? So as long as the multicollinearity for these two variables is relatively small, you may not need to consider including interaction terms in your model, but if these are like, for example, -9 and positive 0.995, then probably including interaction terms is a must, or maybe doing some other modifications to your model may also be necessary as well. Okay, so those are the primary things that you definitely need to know for multiple linear regression, including diagnostic tests such as correlation matrices, added variable plots, and variance inflation factors. So I hope you enjoy it, and I'll see you in the next video. Take care.